So our next presentation is going to be by Connor Hodges from the University of Texas at Austin, who is going to be talking about using sound to see unexploded munitions on the seafloor. All right, take it away.
Okay. Hi, I'm Connor. I'm a PhD student at the University of Texas at Austin, and here to talk about how corrosion affects our ability to detect munitions in the water. So the motivation is there's been more than 400 sites identified by the Navy as potentially contaminated with unexploded ordnances. Um, this is a problem as these sites get transitioned to civilian use, and these areas need to be cleaned up. This isn't just like a partial cleanup of the area. You want to remove all the munitions to prevent any accidents from happening with people. So, of course, these are leftovers due to wartime activities, whether it's dumping or training exercises. So, long-term environmental aging that could impact these structures, these munitions, could be in the form of corrosion, chemical process that turns the metal into an oxide, erosion, physically wearing away of the material, or biofouling, accumulation of microorganisms or organic matter on the surfaces of these objects. My study focuses primarily on corrosion and how the physical structure changes and changes to the material composition of these samples. So the goal is for our research is investigate these impacts with acoustics and how they impact the acoustics, and then be able to provide this information to systems that would be looking for an automated target recovery systems recognition to detect and classify, improve the recognition. So these are the samples that we had. These are the Mark 23. These are cast iron bomblets that were used during World War II. They were by pilots. They practiced. So pilots would fly over and drop them, and they had a shotgun shell with a flare to let the pilots know where they hit. So they've been sitting in the Tisbury Great Pond for about 80 years, which is brackish water pond, and about mean burial depth of 48 centimeters. We had one other sample that was from Duck, North Carolina, but that one was inland, so it had a little bit less corrosion on it. So here you see some of the targets that we have. You see various levels of corrosion, which is really just a product of like local salinity, pH of the area where the bombs were buried. Just where they happen to be, you can have very different samples. So we did acoustic tests on these samples. Here's kind of showing a one aspect angle that we looked at and how we isolated out the data. So when you do that for all aspect angles, we had the target rotating in the water column while we pinged it with a chirp. And then we isolated out just the received signal from the target. So you'll see from the samples we have the nose facing the target, or facing the transducer hydrophone pair. That's around 0 degrees. Around broadside, that's around 90 degrees. That's where the sample was the longest, and it was insonified the most. So this is over here the FFT of all of the time domain data over here. And you'll see similar structures. You see the broadside case where it really lights up around negative 1990, and then also around 0 degrees you kind of see that bend in the frequency information towards lower frequencies. So when we did that over all of our samples, we have a group of clean samples at the top. These were pristine samples, and then we tested it against simple geometries, which were just about the same size, and then the rest of the samples we have are corroded samples. So you can see immediately that the corroded samples have a lower target strength than the pristine samples, and you'll see similar signatures that you see in the pristine but that are lacking in the corroded targets. So what do we do with this data? So one of the ways that we looked at the data was acoustic color correlation matrix. This was a direct comparison of each of the samples with each other, and then we sorted them with their similarity to the pristine sample, one of the pristine samples that we have. So we'll see a couple different groups emerge from this data. A less corroded cluster, and that was basically the pristine target without the tail fin, so you'll see at the bottom. And then a highly corroded cluster that was more asymmetrical blobs, I guess. So one of the points of this was we also did CT scans on all the data to get the inside look of what was comprising these. And one of the samples we got back was turned out to be just debris rock. There was actually nothing in it. So you'll see a bunch of these samples that performed worse than debris rock, which this is in a free field environment that we tested them. So the best case scenario, they're performing worse than debris rock. So something else we ended up looking at was getting average target strengths over all the frequencies, and that's kind of what you see here. This is averaged by all the angles that we ran. Each different line represents a different sample. And this plot shows really the overall average target strength of the samples. It's averaged over all the aspect angles we tested and all the frequencies. And you'll see separations from the corroded targets, from the pristine targets, just in terms of their ability to be detected in terms of target strength. Yeah. And it's kind of important to know what frequency bins to look at if you're looking for these targets. So, So, conclusions, we did acoustic tests on all of our samples, cross-correlated them to directly compare the results. You'll see as the sample corrodes, or the more corroded ones were increasingly less similar than a pristine model. And then you see over certain frequency ranges, the targets have lower returns, which would impact their ability to be detected. So, that's all.
All right, we'll do some Q&A. Any in the room first? Yep.
I think this is a really basic question, so apologies in advance. But how did you get the test samples that you were building or using to figure this out? Did you already have them, or where did they come from?
No, they were provided to us from CERTUP. They sponsored our project, and this was kind of like part of the project was these samples they were given to us. So yeah, that's how they were. They were recovered by divers, so spotted and recovered, and then sent to us. So kind of a cool sample set. I think so.
Yep.
So you had these samples done, or you got them from lakes, is that correct?
These ones were recovered from a pond, off of Massachusetts.
Have you seen any difference in your research of freshwater versus saltwater?
We have right now just one data set, but I assume that the freshwater would have a lower corrosion rate than the saltwater. But I mean, there's a lot of things that can impact the corrosion rate on these samples. Yeah.
And I have a question about, obviously an unexploded ordnance is unexploded, but can you talk more about the risks of them and, are they inert? Do you know when you're going and sending a diver down there? Can you talk more about that?
Our samples inert, yes. I trust the Navy that gave it to us. But for the samples, usually it's professionals that deal with them, and especially recovery. Of course, if you see unexploded ordnance in the water, don't mess with it. Leave it be. Report it, so that way it can be dealt with appropriately.
I was surprised that there were some in Martha's Vineyard just
Yeah.
hanging out in the water.
Yeah, spaces you wouldn't really expect.
All right, and we have a couple of online questions.
Yeah, Anshay Bandari sent a question. How can this study be applied to other types of munitions a civilian may encounter?
Well, what we're looking for would be key signatures to look into that maybe remain consistent for the longest period of time for these corroded targets. Whether that's a frequency range, because you'll see that the total structure can completely change. This is one of the samples that we got, and it's very irregular, it's very porous, and it would be really, it doesn't really look like the target that we have. So ideally, with this set, we get a baseline of key things to key into, and then I'd like to get another set of samples that are also highly corroded, and then be able to check these results against something like that. So yeah, this would kind of get like maybe a boilerplate type method to apply to other corroded munitions that you encounter.
All right, I think that is all the questions. Thank you so much.
Okay, thank you.